Hello, my name is Irina Zenyuk, and I'm an associate professor in chemical and biomolecular engineering in School of Engineering at University of California, Irvine. And today, I will tell you a little bit about future of electric vehicles, and specifically, what types of batteries these new vehicles will carry. Recently, electric vehicles have been in the spotlight. You might have seen that General Motors announced a sale of only electric vehicles by 2035. Also having a flashy "No Way Norway" ad during Super Bowl. California's governor's recent order to ban a sale of gasoline vehicles by 2035 is great news. Battery manufacturing in US is on the rise, and Europe promises recycling plants. Local California companies such as Sila and Rivian make news with technological breakthrough. There are always skepticism of how the electric grid will handle the surge in electric cars. Electric cars are not just technologically driven, but also driven by desire to reduce greenhouse gas emissions that stem from burning fossil fuels. Our economy has shifted away from coal power plant generation towards natural gas and renewable energy. Especially in California, with large installation of solar and wind power generation, our electricity grid can run some days on 100% renewables. However, shift to lower carbon energy has been restricted to the electricity sector. And we are not on the track to cut emissions and to meet the targets agreed in the Paris Climate Accord. Thus, decarbonization of the transportation sector through electric vehicles is much needed. Climate change is caused by increase in the greenhouse gas emissions to the atmosphere. This comes from several economic sectors, with most prominent being transportation, followed by electric power sector, industry, commercial and residential, as well as agriculture. Within the transportation sector, more than 50% of emissions come from light-duty vehicles, less than a quarter from heavy-duty vehicles, such as trucks or buses. Then we have aviation, others, trains and ships. To limit global warming to 1.5 degrees Celsius, well over 20% of all US vehicles need to be electric by 2030. This flow chart is of the estimated US energy use in 2019, assembled by Lawrence Livermore National Laboratory. The vast majority of our energy still comes from petroleum, natural gas, and coal. The transportation sector is the single biggest consumer of energy, accounting for nearly 40% of energy consumed by all four sectors: residential, commercial, industrial including. So not only that, but it also wastes a full 80% of energy, making it only 20% energy efficient. Part of this waste is due to the fact that gasoline cars or internal combustion engine cars are inherently inefficient, as they release large amount of energy in form of waste heat. So what is so different in electric cars compared to internal combustion engine cars? Internal combustion engine cars burn fossil fuels and release carbon dioxide as byproduct. They are highly inefficient and convert only 20 to 38% of energy stored in gasoline to power at the wheels. And depending on the model, are designed for about 150,000 miles. Electric vehicles run on electricity and only, and are powered by rechargeable battery packs, and therefore are inherently more energy efficient, being 77% efficient from grid to power at the wheels. Electric vehicles have no tailpipe emissions. They also require less maintenance with fewer mechanical parts. The downside of electric vehicles is that recharging time is still long. The driving range is still limited, and the cost can be still prohibitive. The lifetime of electric vehicle will depend heavily on the conditions of driving, climate, but generally, one can expect 300,000 miles. That can translate roughly into 20 years of service life. Currently, there are around 1 million electric vehicles on the roads in the United States, and 1/3 of them are here in California. Let's look at the structure of electric vehicle. Electric vehicles have electric motor instead of internal combustion engine. They use large battery pack to power the electric motor. To power the battery, they have to be plugged into wall outlet or other charging equipment. The car does not contain liquid fuel components, such as fuel pump, fuel tank, does not require oil change. For massive fleet deployments of electric vehicles, several challenges exist. The range anxiety, we already mentioned, is probably the most common issue, as electric vehicles are not designed for long duration travel and need a bigger battery to reach long range. Infrastructure and grid reliability is another challenge. It is estimated if we convert all internal engine cars in California into electric vehicles and plug them into our outlets at houses at night, we will require 25% increase in energy capacity on the electric grid. Therefore, for grid to operate effectively, we need to add grid energy storage. Recharging time is still long. Batteries' durability is always a concern, especially when used in harsh climate. Batteries are exposed to mechanical shock and vibrations, as well as wide temperature range. And fast charging discharging rates exacerbate longevity of batteries. The materials availability for the large-scale deployment of electric vehicles is something that we are still trying to determine. The most prominent being lithium and cobalt. We also worry about the supply chain of these materials. Lastly, heavy-duty applications are challenging as trucks will lose about 30% of payload capacity if they run on batteries compared to internal combustion engines, losing also time on recharging. Battery history is long and rich. The batteries that are currently used in electric vehicles are the rechargeable lithium-ion batteries. They are desirable compared to nickel-metal hybrid batteries due to their light weight, much higher energy density, and longer cycle life. These batteries were commercialized first by Sony in 1991. You might know that in 2019, Nobel Prize in Chemistry went to Goodenough, Whittingham, and Yoshino for the development of lithium-ion batteries. Electric vehicles are currently the main source of demand for batteries. More than 2/3 of world lithium-ion batteries are used for electric vehicles and projected to reach 3/4 before 2030, according to Benchmark Mineral Intelligence. Batteries will become even more disruptive across industries as demand grows and cost continues to fall. Asian countries dominate battery market. Nearly 65% of lithium-ion batteries come from China. In comparison, for example, no single country produces more than 20% of global oil output. So how does battery work? Well, a typical cell consists of a negative electrode, sometimes called anode, separator, and positive electrode or cathode. Both anode and cathode are connected to thin current collectors made out of copper and aluminum. And these current collectors harvest electrons. In conventional lithium-ion batteries, anodes consist of graphite material filled by electrolyte, whereas cathodes consist of active material, which is typically lithium metal oxide, conductive carbon, and binder matrix. So during discharge, lithium comes out of the graphite and splits into electrons and lithium ions. Lithium ions transport through the electrolyte, through the separator, to the cathode, and electrons transport through the external circuit. And because they transport through the external wire, they can be collected as a current, and they can power a device or electronic motor. So once all lithium moved from the anode to the cathode, the battery now is discharged. So what happens during charging process? Well, to charge a battery, reverse process happens. Now we use external power to make transport happen. Lithium has its lowest energy state in cathode, so it will not voluntarily move from the cathode. So we need to apply power to force lithium to go from the cathode to the anode. So thus, when we apply a current, electrons transport through the external wire. The lithium transports through the electrolyte and the separator, and thus the battery now again is fully charged. Let us briefly talk about how to determine energy of battery. But to do that, we first need to learn about battery capacity. So when electron transport, they carry current, and units of current is amp or ampere, where 1 amp carries 6.24 times 10 to the 18th electrons per second. The measure of battery capacity is current times time, has units of amp times hour. For example, if we connect a battery to external load, the load will determine at what current we will be draining battery. The battery rating typically comes as a capacity. For this US manufactured battery, the rating is 2500 milliamp hour. This means that if we supply 2500 milliamps or 5 amps, we can discharge this battery in 1 hour. If we use half of this current through the load, the battery will be discharged in 2 hours. If we double the current, or if the load needs 5 amps, the battery will be discharged in half an hour. That's very fast. From these calculations, we can determine battery life. So it's a ratio between battery capacity and the load. So now that we learned about battery capacity, let's compare two batteries that have the same capacity but different voltage. The same US manufactured battery operates at 3.7 volts, whereas the battery pack that we see on the bottom operates at 9.6 volts. Both will deliver 2500 milliamps in 1 hour, according to their capacity. How about energy stored in these batteries? If we multiply the capacity of the cell by voltage, we will get units of watt hour, and this is energy. So the 3.7 volt battery will produce 9.25 watt hour energy, whereas 9.6 volt battery will produce 24 watt hour of energy. Energy of battery depends on both capacity and voltage. Generally, voltage depends on chemistry, but several cells can be combined together to reach higher voltage and thus higher energy. Let's introduce a few more concepts. Power is the rate of energy drainage. A lot of times we hear about power density or energy density. Energy density is defined as energy divided by mass. Thus, for electric vehicles, we want large energy density, not necessarily energy. as electric vehicles have to carry their own weight. Whereas for stationary applications, like grid storage, we care about energy, not necessarily energy density, as weight is not as much of an issue now. Energy can be similar for devices operating at different power scales. For example, 1 watt light bulb operating for 12 hours will consume 12 watt hour of energy, whereas a charging station with 1 kilowatt will deliver the same amount of energy if it charges electric car for only 1 minute. If you look at this power scale, wind farms operate at megawatt scale of power. Peak power generation of Hoover Dam is in gigawatts, and average total power consumption of our world of total power consumption in 2013 is around 10 terawatts. On this scale, 10 kilowatts is the average power consumption of electric car on EPA's highway test schedule. But you probably care more about maximum power of electric vehicles, right? So Tesla Model S can operate at 825 horsepower, which translates roughly to 615 kilowatts. In comparison, Porsche Turbo S has 761 horsepower, which translates into 567 kilowatts. Well, last time I checked, the drag race between these two cars was a close call. Typically, in physics, we use joule as energy unit. But in batteries, our convention is to use watt hour for energy. And here, 1 watt hour is equivalent to 3,600 joules, which is a large number. Thinking of electric vehicles, power is needed for electric vehicle acceleration and climbing the steep slope, whereas energy is needed for long duration travel. Now, let's look at the energy density of modern batteries in electric vehicle. On this plot, x-axis plots specific energy and y-axis volumetric energy density. So Nissan Leaf has around 22 kilowatt hour battery pack, whereas Tesla Model S has 85 kilowatt hour energy in their battery pack. Currently, battery chemistries can only increase energy density not much beyond 200 watt hour per kilogram. Silicon anodes are promising and can reach 300 watt hour per kilogram, somewhere here. Only lithium metal, shown here in red, can enable higher energy density batteries. So notice I differentiate between lithium ion and lithium metal. We'll learn about these differences in a few slides. So by using lithium metal batteries, for example, for system mass of 100 kilowatt hour vehicle pack, we can reduce its weight 3 times. However, no electric vehicles currently run on lithium metal, as there are some technological issues that still remain, such as lithium dendrites that we'll talk about in the next slides, and also battery cycle life. So let's talk about the differences between standard lithium ion battery and lithium metal battery. As a reminder, a lithium ion battery uses graphite as a negative electrode or anode. Lithium metal batteries eliminate graphite electrode and uses thin film of lithium instead. They also remove liquid electrolyte from the cell, and these batteries are called solid state batteries. Electrolytes are flammable, and thus their removal results in significantly enhanced safety of the batteries. Solid state batteries don't catch fire. Further weight reduction can be achieved using anode-free batteries. But all lithium now will be stored in the positive electrode or the cathode, and on the anode, we will just have thin copper foil. So generally, solid-state batteries can significantly enhance the energy density and further lower battery prices. Well, the value of such a breakthrough could be measured in billions of dollars, if not trillions. As I mentioned already, dendrites, right? Lithium metal batteries are poisoned by these lithium dendrites. These are tree-shaped lithium growth on the anode during battery charging. That's when lithium comes from the cathode and transports onto the anode. As it transports there, it plates in the shape of dendrites or trees. As these dendrites grow and pierce the separator, they create so-called short, and battery loses its full capacity. It can also result in overheating of battery. We also call this catastrophic failure of battery. Before I introduce you to my research at UCI and how we try to fight these dendrites, I'll need to tell you just first a little bit more about shapes of batteries. A cylindrical cell, which you're probably most familiar with, consists of sheet of anode, separator, and cathode. They are sandwiched, rolled together, and packed into the cylinder-shaped metal can. These were the first mass-produced batteries, still most popular today. They have many advantages, including mechanical stability, automated manufacturing, and uniform internal pressure. Similarly, prismatic cells, also the same process applies. They have sheets of anode, separator, cathode, all rolled together, but now packed instead of a cylindrical shelf into hard plastic or metallic housing of a rectangular shape. The advantage of this cell design is that box-like shape enables optimal use of available space within car, for example. Pouch cells don't have solid enclosure, use flexible foil as a cell container. The electrode and separator are stacked instead of rolled. Cell swelling can occur after extensive cycling, and at UCI, my group works with both cylindrical and pouch cells. So to solve the problem of lithium dendrites in lithium metal batteries, my group uses a technique called X-ray computer tomography to try to understand what happens inside the battery as we cycle the battery. And it helps to diagnose failure mechanisms for all types of batteries. If you did medical MRI, the X-ray CT uses kind of similar concept. X-rays come from the source and then are transmitted from the source and absorbed, some of them absorbed by battery, and the remaining are detected by the detector. Technique is 3D, requires sample to rotate 180 degrees to obtain internal 3D structure of battery. Here are two examples of our imaging of cylindrical cell. You can see this is 3D rendering of internals of cylindrical cell, where you see the roles of an anode, cathode, and electrolyte, where anode and cathode look bright and electrolyte is darker. And on the right-hand side, you see all the metal components inside the cell, where you have this very large tabs as current collectors that are welded into the electrodes. Challenge with lithium imaging with X-rays is that lithium is very light element. So it's not going to be detected by X-rays. So, but at UCI, we developed techniques to actually detect X-rays, detect lithium with X-rays. At UCI, my group uses the technique as I described, X-ray computer tomography, to probe dendrites in actual real cells. So here is an example of dendrite growing on the anode, and also dendrite as a three-dimensional structure. So while charging the battery, we managed to probe lithium plating in real life. Here is just a snapshot of the lithium dendrite, but we have the full 3D images of all the lithium battery. So looking at this interface, you can see that lithium plates very inhomogeneously. First, it nucleates, it forms these little trees on the surface. Then these trees, I'll play the video again, they merge together into this film, very porous lithium film. And then as we move lithium back from the anode to the cathode, this lithium film kind of moves along the surface more like a liquid rather than solid, which is quite fascinating. We are the first group to show this as the battery is operating. Other groups have looked at lithium in ex situ or just looking at lithium, but not when battery operates. And finding this kind of behavior where lithium behaves in between liquid and solid can help us understand how this dendrite growth happens. And as we understand why dendrites grow and how they grow, we can eliminate it, and we can eliminate them as a problem and help engineer better interfaces without dendrites, and thus enable solid state battery technology. So the research I showed thus far is done on small cells. With a generous gift from HORIBA, coordinated by former Advanced Power Energy Program Director Professor Samuelson, we opened a new institute directed by Professor Stamenkovich in engineering. Here, we'll be able to study with X-ray CT and other characterization, not just small cells, but kilowatt-hour stacks that actually go into electric vehicles. Not only that, we'll be able to cycle them in a room-sized environmental chamber, and also we can put electric vehicle on the dynamometer and see how batteries cycle inside the electric vehicle. The facility is one of a kind, and it will enable UCI to lead in the fields of electric vehicles, but also in the fields of connectivity and vehicle autonomy. Lithium metal or solid state batteries will resolve range anxiety for electric vehicles, will partially solve materials problem as less materials will be needed to achieve the same energy density, and we will push lithium batteries towards heavy duty applications as higher energy density will be possible. From the cost perspective, currently the prices of batteries is around $175 per kilowatt, which is about 10 times less than the cost in 2010. And the cost is projected to decline further due to improving technology and higher volumes of production. For example, to achieve 300-mile range electric vehicles below $40,000 of cost for electric vehicle, we need batteries to have energy density of 350 watt-hour per kilogram. And this can be achieved only with lithium metal batteries. And the battery pack cost will be, for this scenario, below $125 per kilowatt hour. So solid state batteries can meet these targets, and already several companies have promise of solid state batteries with lithium metal. For example, Solid Energy Systems has demonstrated pilot scale pouch cell with 450 watt-hour per kilogram energy density. The lithium metal batteries will also meet a battery pack cost due to smaller battery packs needing for the same driving range. So I hope today you learn a little bit more about electric vehicles and batteries in general. Electrification of transportation sector is just the beginning. As the climate crisis introduces record heat, more fires, fast rising seas, action is needed to cut greenhouse gas emissions across every part of economy. To enable broader deployment of renewable power generation, such as wind and solar, we need long duration grid energy storage. While batteries will be effective for hours range, new solutions are needed for months or seasonal storage. Pumped hydro is one of the solutions, but is geographically constrained. Recently, Europe introduced massive programs where hydrogen is used as energy storage and conversion medium. It can be used for sectors such as chemical manufacturing industry, metallurgy sectors, cement, steel. It can also be used for as seasonal grid energy storage. Transportation sector will be the first one to achieve electrification and deep decarbonization through deployment of electric vehicles. And I'm looking forward for this transformation to happen. We are looking for exciting times to come, and UCI will be one of the leading institutions to lead this transformation. Thank you.